Welcome to the Fusion Note, a weekly dose of breakthroughs, curiosity, and connection, because the future is better when we build it together. Today, we're kind of embarking on what we call the Feynman path. It's a deep dive into breakthroughs driven by, well, ignoring labels and really questioning the answers we think we know.
Right. And what's so essential about Feynman's whole approach is understanding that difference. The
Yeah.
difference between knowing the name of something and truly knowing it. He
Mm.
talked about his father teaching him about a bird, not its label, but watching how it flew, what it did.
The behavior.
Exactly.
Yeah.
Real knowledge means you could explain the core thing, the mechanism, simply,
Hmm.
maybe even to a child. If you can't, you probably just learn the label.
And it seems when you have that level of curiosity, you start seeing the underlying beauty, the structure of reality. Our sources definitely point to this deep elegance, like whether it's the patterns you see when waves collide or even how stalagmites grow. The beauty we see is, well, it's tied directly to clean mathematical laws. So let's unpack this curiosity, see where it's leading to some really big results. Starting with the energy race, we're seeing just incredible acceleration in fusion power lately.
We really are.
Helion energy, for instance, they're moving fast on that 50-megawatt Orion reactor, the one near Richland, Washington.
Right.
They're aiming for net energy, get this, by 2027, and mainly to power huge users like Microsoft's data centers.
And what's really insightful there, strategically, is the shift. This isn't just slow government funding anymore.
No.
It's being pulled forward by specific industrial demand, and the solutions are getting really sophisticated. AI is becoming crucial.
The AI angle?
Yeah, Google's DeepMind, they've partnered with Commonwealth Fusion Systems, CFS, the Spencer Tokamak folks.
Okay.
They're basically throwing advanced machine learning at it, using AI to solve the super complex physics needed instantly to control that incredibly hot plasma inside the reactor.
Which has to cut down the timeline dramatically.
Oh, absolutely. It shaves years off, a total game changer for controlling the fusion reaction.
So that's the huge scale challenge. But if we follow that Feynman path down to the quantum level, we find these revolutionary new ideas for energy, too. Researchers were questioning the limits of standard silicon, right? And they found this organic, radical molecule, P3TTM.
P3TTM, yes. And this molecule, it does something pretty special. It exhibits what's called Mott-Hubbard physics.
Mott-Hubbard physics. Okay, what does that mean in simple terms?
Yeah. It's fascinating because it describes a specific kind of electron behavior that was historically really hard to actually use. Basically, it helps maximize how efficiently electrons get knocked out of a material when light hits it.
Okay. More bang for your buck from sunlight.
Pretty much. And by applying this sort of quantum secret, they built a really simple solar cell using this P3TTM stuff. And it achieved almost 100% charge collection per photon.
Wow, nearly perfect efficiency.
Yeah. Which opens the door for potentially hyper-efficient, really lightweight solar panels that are also cheap to make. Amazing potential there.
Okay, so connecting that pursuit of perfection in physics to biology.
Hmm.
Let's look at health breakthroughs, specifically this idea of goal-directed morphogenesis.
Mm-hmm.
It's a concept from Dr. Michael Levin that's frankly kind of mind-bending. He's suggesting aging isn't just damage building up over time.
Right, not just wear and tear.
It's more like the body loses the active goal state, the blueprint maybe, that it was programmed to maintain after we finish developing.
Exactly. The source material really digs into this idea that our biological hardware has this hidden control system. It's
Bioelectric signals.
Yes. And if we can figure out how to apply targeted bioelectric interventions, we might just be able to sort of reawaken those latent regenerative programs, essentially telling a tissue or an organ to reread its original instructions.
Like hitting reset on regeneration.
Kind of. And this isn't just theory. It's moving into commercial projects. Things like Anthrobots, programmable living robots made from your own cells for targeted repair.
Wow.
And also Celjavu, which is trying to use similar methods to overwrite cellular drug resistance in things like cancer.
Incredible potential. And while we're on innovation that could have global reach, we should mention that 3D printed water from air device.
Oh, yeah, the student project.
Developed by German students. Yeah, it's just a beautiful example of low-cost ingenuity. Simple, portable parts, basically a passive condensation chamber, and it yields about 6 liters, 1.6 gallons of clean drinking water every day. Just pulls it from the air, off-grid solution.
Really elegant in its simplicity.
Oh, yeah.
So stepping back, what does all this point to? We've seen breakthroughs at every level, right? From tiny quantum efficiencies
Right.
to potentially regaining control over biological aging.
And it all seems rooted in that deep Feynman-style curiosity.
Yeah.
That willingness to ask, hang on, what if the limits we accept aren't really limits at all?
Which brings us back to that question Feynman himself asked. He said, poets say science takes away.
And his point was, by understanding the math, the physics, the language nature speaks, you see far more elegance, not less.
It definitely raises this powerful idea. If reality does operate like this structured quantum artistry, full of potentials just waiting for observation, then maybe pursuing knowledge, that deep curiosity, is the ultimate aesthetic act, finding the beauty in how things actually work.
So, a final thought for you, our listener. If reality is this canvas of potential, what observer choice are you curiously awaiting to collapse into meaning this week? Go explore the world with new eyes.